Hi, everyone. Welcome back. Very quickly, so we're going to take the questions at the end of the talk. So I'm now handing over to our next speaker, Joerg Teschner, and he's going to talk about geometric characterization of topological string partition functions.
Yeah, thanks very much for the introduction, and thanks to the organizers for setting up the conference in such a nice way under unusual and in some respects probably difficult conditions. What I want to talk about is joint work with Joanna Koman, Pietro Longhi, and Eli Pomuni. And yeah, so let me jump right into the problem. So here, yeah, I'm trying to formulate the problem we have been trying to address, which is to get a, well, ideally geometric and analytic characterization of topological string partition functions. So what we will consider is A or B model topological strings on Calabials manifolds. Say when we talk about A model, we would call them X, otherwise Y. And good, in the B model, the worldsheet definition would yield a priori formal series like here, where we sum over genera. So there are contributions of all genera to the topological string amplitude or topological string partition function. And well, in general, it is not clear if this can be actually summed to represent an actual function or anything alike. So this is the question, do there exist functions having this series here as asymptotic expansion? And of course, this comes with obvious questions, namely, if so, which space are these functions defined on? And secondly, well, do we really want a function or maybe a section of a line bundle or something even more general? In any case, yeah, even a semi-optimistic scenario would be that the z-tops, which are defined by a summation of a sort of the series, could be locally defined functions on, well, depending on whether we talk about A or B model, either the Kähler moduli space or the complex structure moduli space of the Calabials in question. So if, for example, we're talking about the Kähler moduli space, then we would be considering this as a locally defined function of, say, a collection of coordinates on the Kähler moduli space. So this would yield a concrete representation of this object. And yeah, so somehow the main theme of this talk is going to be whether there may exist natural geometric structures on, well, we will mostly focus on the complex structure moduli space, but of course, the other guy is related by mirror symmetry, allowing us to represent the top as a local section of a sort. And for a class of local Calabials manifolds, we shall offer, that is, propose such a description. And I will, towards the end, hopefully discuss a few hints that such a discussion could even generalize beyond the class that we consider here, which is defined as follows. So we consider local Calabials defined by equations of this form. So we have here four complex variables related by one equation, uv minus some function f sigma of x and y equals to 0, which is such that well, the two-dimensional curve, that is one complex dimensional curve defined by just setting this function f sigma of x and y to 0, is, well, a subset of the cotangent bundle of some Riemann surface, so which we assume to be given once and for all. And we have in addition a quadratic differential on that Riemann surface. And so this here would be a curve in the cotangent bundle of that Riemann surface defined by a quadratic differential, which then in turn defines a local Calabials by this equation. So this is some, well, reasonably interesting and large class of local Calabials, which have appeared in the context of geometric engineering of the so-called class S theories that we just have heard about in Tomoyuki's talk. Now, what is the complex structure moduli space? Well, that's pretty obvious by the description I just gave of these local Calabials. It is the space of pairs C, the Riemann surface, that is the complex structure, of course, matters, and Q, the choice of a quadratic differential on that Riemann surface. That is the concrete representation of the moduli space of complex structures in the case of our interest. This immediately comes with some important geometric structures, which, well, come almost for free by this very description I gave. Namely, quite important is in particular the special geometry, which is familiar from Cybek-Witten theory, where we can take the periods of the square root of the quadratic differential, which would be called the Cybek-Witten differential, as coordinates, and there is a relation between these coordinates allowing us to introduce the prepotential as the potential, giving us here the, say, conjugate or dual set of periods when we start here with the periods over a basis for the first homology of this curve sigma. A canonical basis which has here, well, a polarization built in. Well, secondly, what's going to be important is that this setup basically comes with an integrable structure for free, as was pointed out by Donaghy and Witten, and then encoded in a rather general theorem by Dan Fried, namely associated to the geometric structure called special geometry. There is canonically a integrable structure. Basically, we can, over each point of the base manifold, which here is identified with moduli of complex structures, define a torus by basically this equation, where here the main data parameterizing the the geometric structure of the torus is the period matrix tau, which in turn is the matrix of second derivatives of the prepotential. So this is then defining a torus fibration, so we can project this moduli space M int, well, where int can stand for integrable or for something else, which I will mention in a moment. We can project it down to the bases, which are the moduli of complex structures. Yeah, so this is equipping it with what we can call an integrable structure. Three other pictures or incarnations of this moduli space will be of some importance. Well, here we have these tori. I mean, we can identify these tori with the Jacobian or prim varieties of this curve sigma. And via Abel-Jacobi maps, that is some classical algebraic geometry, of course, there's a one-to-one correspondence between points on these torus fibers and the divisors on sigma. So I can identify this moduli space with a moduli space of pairs, where we have on the one hand the curve sigma, and on the other hand the divisor d, associated to these points, well, b here by Abel-Jacobi. And it is this type of geometric object is rather familiar from a theory of the Higgs pairs initiated by Nigel Hitchin. So there's an isomorphism via a famous construction of Nigel Hitchin's of, well, the moduli space of Higgs pairs, holomorphic bundle, and Higgs field phi to this moduli space of pairs sigma and a line bundle on it, or equivalently a divisor on it. I'm here, of course, skipping some details, which in general will be relevant. And say for the embedding in the, say, Calabials context, it's also important to remark Diaconescu, Donaghy, and Pantev have identified this moduli space in question with the intermediate Jacobian fibration, which, well, one can define quite generally in the context of Calabials manifolds. And yes, what was shown is that if you specialize it to the class of local Calabials we are considering here, it would reproduce the Hitchin's description of the moduli space of Higgs pairs. Okay, so that's the playground we want to work with. This is the class of examples for which sort of we have a reasonably concrete story, a reasonably concrete prediction or proposal to make. Okay, so this slide is to summarize basically our approach or our starting point before we summarize sort of the main outcome of our investigations. So basically what we started from, and which then basically also yields confirmation of the proposal we're about to make, are the observation that some of these local Calabials can be represented via limits that are familiar from the geometric engineering of gauge theories and string theory as limits of toric Calabial. And when this is the case, then we can compute the z top with the help of the topological vertex. Of course, we need to take the limit. This needs a little bit of care, but in any case, it can be done for a subset of the y sigma. I don't know if it can be done for all of the y sigma, because, for example, in higher genus cases, I wouldn't know how to do the geometric engineering of this class. But anyway, we have a few examples where we can do that, and there we can compute and compare. Well, then it's a reasonably old and famous story that what you compute with the topological vertex can be compared to results of the instanton counting as developed by Moore, Nekrasov, Shatashvili, Losev, Nekrasov, Shatashvili, and Nekrasov. And then combined with the AGT correspondence, one finds that, well, the concrete computations with the help of topological vertex, what they actually produce are conformal blocks of the Virasoro VOA at c equals to 1. That we have a rather special central charge is, well, due to the fact that in this context, we're not going to talk about refinement. So we have, and this is appropriate for really having this geometric picture of the topological string, etc. So this is the case we are. And then there is also a reasonably old and famous story relating the z top in this case to a counting function of d0, d2, d6 branes. And then furthermore, by appealing to further string dualities, the prediction was made by Dijkgraaf, Holland, Sulkowski, and Waffer that you can arrange by doing this somewhat funny transformation, which will play a very important role throughout the whole talk. You can sort of basically take a transform of the z-top, the object we're interested in, where you, well, this is if you here just redefine variables to have an I. It's like a Fourier series, but with very special Fourier coefficients. So this object, on the one hand, should then also be related to a counting function where you also are counting the d4s, which is related here to the p. And then the main prediction based on string dualities of Dijkgraaf et al. Was that this object should have a representation as a free fermion partition function, basically on that curve sigma that we started from, that basically was defining our local Calabials. So this would be nice in reducing really the computation that we want to do to the computation of free fermion partition functions. And well, this of course could bring into the game, well, all the nice relations between free fermion partition functions, tau functions, integrability, and so on and so forth. And some, well, modern variant of this plays indeed an important role in our story. Let me stress that, yeah, in general, you can invert this relation. So you should be able then to recover the z-top by inverting this relation from the free fermion partition function. And that is sort of the attitude we're taking here. And then what we used was recent progress on the relations between free fermion conformal field theory, tau functions, and Virasoro VOA, which was stimulated in the paper by Gamayun, Yorgov, and Lissovy. And the version, I mean, this was proposing a conjecture basically relating giving a new description of the isomonodromic tau functions in terms of Virasoro conformal blocks. And this conjecture was then proved in joint work with Yorgov and Lissovy. And yeah, this gave some interesting interpretation of this series in particular, which I shall return to perhaps a little bit towards the very end. But in any case, this is sort of the background. These are the tools we were using. And then, we were trying to interpret the results of all that in geometric terms. And this led us to the picture I want to formulate now. So here is the proposal in a nutshell. So really now I want to sort of throw a little bit away the ladder we climbed up on and formulate in as geometric terms as possible what the resulting picture is. Down here, you're seeing again this formula relating the top, the object we are ultimately after, to a tau function. So this really is a kind of refinement of the formula we just looked at here on the previous slide, relating the z top to free Fermat partition function, where of course you should think of now here the left-hand side being the free Fermat partition function. Good. In any case, so what geometrically are our main players? It is on the one hand the moduli space of complex structures on the Calabial in question, and then the torus fibration that, thanks to special geometry, is canonically associated to the special geometry of these moduli space of complex structure. So that would be the intermediate Jacobian fibration. The claims are, there exists on the one hand a canonical one parameter, and the parameter h bar here is identified with the topological string coupling constant. A canonical one parameter family of deformation of the complex structures, which will be defined by producing an atlas of Darboux coordinates on something which is reminiscent of twistor space. And ultimately, I believe it is related to some twistor space. Maybe I have some comments towards the end, but yeah, in here it is just introduced as the product of M int tensor well, times the product, Cartesian product with C star. And secondly, and here come the main players, namely a line bundle with a connection. And yeah, the main point is the way how we describe basically how this object here, the tau function, changes from chart to chart. The claim is going to be, and I will detail this, that the transition functions are basically canonically defined by the changes of coordinates from one patch to the other. So therefore, the very data defining this atlas, thereby defining the deformed complex structure, canonically also define these transition functions, defining the line bundle as a variant of the generating functions, which we call difference generating functions. This is just because, yeah, the usual derivatives in generating functions from symplectic geometry will be replaced by taking finite differences. I will explain how. So these are then what represents the transition functions defining the line bundle, and then say the flat sections of the connection, well, these are our tau functions. And good, so this is basically what defines the left-hand side, and then the claim is that for all of these charts, we do have such a Fourier series expansion defining here the z top we're after as the Fourier coefficients on the right-hand side. So this is the claim in a nutshell, and of course I owe you more explanations about the ingredients here, which I want to do in the next few slides. Okay, so first of all, there is the story of how to define a, say, well, H-bar deformation of the complex structures we're starting from. And this is going to be a game that has appeared in a priori different looking context, which is the work of Gallotto, Moore, and Neitzke. And well, the variant of that that we're using here and discussing here is what appeared in more recent work of Tom Bridgeland. Well, for those who know about this, it is basically what is called the conformal or massless limit of the story of Gallotto, Moore, and Neitzke that is of relevance here. So we want to define the H-bar deformed complex structures by an atlas of coordinates on the space here we have been talking about, a collection of charts. And in these charts, we have Darboux coordinates, and well, these define the complex structure in the usual sense, namely for each value of H-bar, then we declare these here to be, well, holomorphic functions with respect to the such defined complex structure. You may note I have a little more than one maybe usually has, namely there is a polarization built in, which is kind of important because the polarization is going to used here basically in this formula where we have, well, the x check coordinates here and the x coordinates here. So, I mean, we need a polarization to write down such a formula. Good, then the important thing is basically, or the most important thing is, of course, to describe the changes of coordinates from patch to patch. And the point is, this is, or the claim is, this is going to be given by also quite familiar formulae from the work of Gayotto-Muir-Naitzke, namely, this is represented by cluster-like coordinate transformations. So we have a rather simple rational form. When we take exponential functions of these coordinates, little xi, there's a little bit here of notation. So we have a charge vector here, also split according to some polarization, which we, with some symplectic form, contract into the coordinates xi, which again are arranged into such a vector. But yeah, it's basically defined by explicitly writing out the result as notation that is handy in order to write the changes of coordinates into a compact form. And the crucial data here are some rational invariants, which are piecewise constant then over the moduli space here we're talking about. So these are these rational numbers omega of gamma, which are subject to the so-called Kontsevich-Solomon wall crossing formula. So there are some constraints which basically, you could be seen as constraints for the very possibility to define a consistent, deformed complex structure in this way. This appeared as smoothness condition in the case of hyperkähler metrics in the work of Gayotto-Muir-Naitzke. Here we're talking just about the complex structures. Last but not least, and of course I have to be somewhat sketchy and schematic here in view of time, but yeah, what is relating the new coordinates to basically the old coordinates for the base manifold, which were here defined as these periods. We have had these special coordinates for the space of complex structures, that is the base of the torus vibration before. And so now the requirement is that when we send h bar to 0, then as the leading term, we recover those. And quite interestingly, and I don't have the time to go into much details about this, then as sort of the next to leading bit, we find coordinates for the torus fibers. Here is the more precise relation. There's a little bit of redundancy, which however turns out to be inessential in some precise way. So anyway, this is the asymptotic behavior, where then the actual coordinates for torus fibers are some combination where again tau is the period matrix defining these, the complex structure of the torus fibers. Okay, so this is, if you want, defining, and there is more sophisticated formulations of this, but the problem to find, given the data omega satisfying Kontsevich-Solomon wall crossing formula, then these coordinates, this can be called a variant of the Riemann-Hilbert problem, and that is the point of view, going back to Gayotto-Muir-Naitzke and more recently further developed by Tom Bridgeland. There are two known ways to solve this problem. On the one hand, the work of Gayotto-Muir-Naitzke gave a solution by, in terms of nonlinear integral equations. So whenever you can solve these nonlinear integral equations, which you can often do by iteration, and there are in some cases results concerning existence and uniqueness of these NLIE, well, then they basically produce from the given input data, which are here our coordinates A and theta, then the desired coordinates x sub gamma of h bar, which represent the solution to the, BPS Riemann-Hilbert problem. That's how I sort of want to call it for having handy terminology. There's a little trouble here in this case with the NLIEs. I think for the case at hand, which is this conformal limit, the convergence typically of those is relatively slow, and I am not sure if, say, the results on existence and so on would hold in this case. Typically, I think it requires what is called massive deformation. So therefore, but I think, yes, ultimately for the theory, it is important that there should be this other way of representing the solution. anyway, there's a lot of like mathematical problems that sort of, I do not claim that here, especially in this part, everything is already rigorous mathematics at this time of, what I want to focus on is the second way of solving it, which uses something which is called quantum curves, and I will elaborate on what this is. And well, for the moment, let's just think of differential operators of this form, which basically are built from a deformation of this quadratic differential, which was defining our curve sigma in the first place. What kind of deformation I will mention in a moment. And then the basic idea here is that the coordinates we're after, the solutions to this BPS-Riemann-Hilbert problem, would be defined by employing the Borel summation of exact WKB solutions of the differential equation that you can, well, define from this differential operator, that is whatever is annihilated by this differential operator. This is then what allows us to define these coordinates. So this is the basic idea, but we're going to talk about this a little more in, well, the next few minutes. So the basic idea here behind is, well, we were basically defining our curve sigma by some equation of the form y squared is q of x. And well, there is a canonical symplectic structure here where y is the conjugate of the variable x, which is a local coordinate on the curve sigma. What this very much suggests is to do the canonical quantization in order to introduce the h bar, which is then just in schematic form amounting to the replacement y by h bar over I d by dx. So then from this equation, what we get is exactly this differential operator that we already saw on the previous slide. And well, what this is basically describing is a class of holomorphic connections called operas. So there is a whole well, theory about generalizations of this type of differential operators, which, well, is not so important for what I'm saying today. And what is important is that there is an essentially canonical generalization which basically deforms, h-bar deforms these pairs sigma d, which then was representing, according to the previous discussion, this torus fibration. This comes by allowing apparent singularities. These are singularities which in PSL2C have trivial monodromy. And you see, these have a very peculiar form with here the leading term in the Laurent expansion having a 3/4. And then if we're careful here about powers of h bar, it is down by a power of h bar squared. So if we just formally turn off h bar, so send h bar to 0, all these apparent singularities would disappear. So this basically is natural and is related to this fact that also here these coordinates on the torus fibers came basically at the next to leading order of h bar. So basically also here the dependence on the new variables, which are the positions of the apparent singularities, basically comes in higher orders in the h bar expansion. There's a relation between this, but I don't have the time to go into much details here. I have discussed this elsewhere, or you find the discussion in the papers. So this is what we want to study, operas with apparent singularities. That is, the QH bar has apparent singularities of this type. All right, so the conjecture then is that the solution of this, what we call BPS-Riemann-Hilbert problem, is given by the composition of the holonomy map with particularly nice, that is, rational coordinates for the space of monodromy data, which is what is called the character variety. That is the algebraic variety having as the coordinate ring the trace functions, traces of holonomies or monodromies of this differential operator. And we want very special such coordinates. So first of all, we want coordinates which give us the trace functions, as rational expressions of the coordinates. And secondly, we want them to have a Borel summable h-bar expansion. And basically, the idea, the main claim is this is, basically uniquely determines coordinates. So this determines very distinguished coordinates, and these very distinguished coordinates are these very distinguished solutions to the BPS Riemann-Hilbert problem we're after. So we're not having here any like freedom of coordinate choice. In the end, we want a canonical coordinate choice determined just by the data that we put in. All right, so something about exact WKB. So what are the essentials we need to know about that? So we're talking about solutions of the differential equation defined by the quantum curve. That is this differential equation here on the top right. Good. It is, of course, well known how to expand the solutions into powers of h bar. This gives us series of this form. So we can write it as an exponential of some integral, and the integral is a function that is determined from the Q by something called the Riccati equation. So the S is the solution to the Riccati equation. You can solve this equation easily as a formal series in h bar. The leading term is going to be here our square root of Q0. And so, well, this gives us a formal series. We're then taking, well, we're having here in the leading term a choice of sign, and we're going to take an odd combination of the solutions determined by either choice of the sign in order to define here this, this function S we're integrating over. So this gives us a standard way to construct in a series expansion in powers of h bar the solutions here to this differential equation. Now, there are some results. Unfortunately, the status of these results is a little, well, unclear. But, well, I think there is little doubt that these results are ultimately correct, which would say that this series here is, in fact, Borel summable. That is, it canonically defines an analytic function of our h bar away from Stokes lines. What are the Stokes lines? The Stokes lines are defined by the equation that the imaginary part of sort of a canonical coordinate that you can define here from the square root of Q by just taking this, well, the primitive thereof, and here we're taking with, well, we're modifying the phase of that, that this imaginary part of, and so this decomposes the Riemann surface into regions. And yeah, within these regions, so if we stay away from these lines, then we have Borel summability, that is canonically defined solutions chi of that form. And yeah, the guys we're after, which are sort of in this way canonically defined by what we put in, are called Worosz symbols. So under these conditions, the type of conditions I mentioned, they can be Borel summable. And if they are Borel summable, then they can represent the ingredients to the solution of the BPS Riemann-Hilbert problem we are after. So there are proofs attributed by many papers to unpublished work of Koike-Schäfke here of Borel summability, and Nikolaev, I understand, is preparing an independent proof, hopefully to appear soon. Okay. So, well, the Borel summability, by what I just said, depends on the topology of the Stokes graph formed out of the Stokes lines, where you basically plot these Stokes lines here, the solutions of these conditions, which start at branch points of this covering defined by the quadratic differential Q. Two extreme, in a sense, cases are of interest. You can, on the one hand, have the case, which is kind of the most generic case, where the Stokes graph defines a triangulation of C. What is here on the right in the pictures are some Stokes graph for 3 punctured spheres. Well, maybe I should enhance it. The punctures are these little blue dots here, here and there. So there are 2 punctures and one is at infinity. And when you then just connect the punctures in such a way that you stay in a Stokes region, then you will get a triangulation of the Riemann surface C. Graph and triangulations of the surface C. For a special choice of the quadratic differentials, you can have another type of Stokes graph, which has basically only, well, saddle connections, that is Stokes lines starting and ending at the branch points, yeah, for its definition. And what they define, if you have, well, a more general situation with a Riemann surface, they define a Pan's decomposition of that Riemann surface. So you have these two, I mean, as the two cases of triangulations and Pan's decompositions, they are associated to corresponding types of coordinates. So Wörth symbols would then always correspond to coordinates. In one case, they're known to correspond to the Fock-Wontroff coordinates. That's the case. That's what is associated to triangulations of C. And in the other case, as was also pointed out in work of Hollens and Kneitzky, in the other case, we have Fenchel-Nielsen type coordinates. That is, coordinates which restrict, when we go to a real size, to the Fenchel-Nielsen coordinates from Teichmüller theory. So there is a nice situation, and well, much of, say, there's a lot of mathematical work already on the cases where we have triangulations as Stokes graph. In particular, Dylan Allegretti has proven the conjecture of Tom Bridgeland's that for that case, the Wörth symbols are Fock-Wontroff type coordinates solving the BPS Riemann-Hilbert problem. But for us, it turns out, and that was sort of causing us considerable headaches, that what we need really is the extension of all that to these other cases, where we have Fenchel-Nielsen type networks and Fenchel-Nielsen type coordinates, which are associated to Pence decomposition. That is interesting in particular. I mean, well, the corresponding quadratic differentials, they're also called Jenkins-Stribel differentials, and these are what we need in order to really extract, say, the topological string partition functions, which we can compare to topological vertex computation. So this case is of particular interest.
Sorry to interrupt you, 5 minutes.
Thank you, yes. Okay, so, well, let me therefore turn to the second half of our proposal, which is that there's a canonical pair of a line bundle and a connection where sort of, yeah, which is basically defined by its flat sections being the tau functions, and the tau functions are the objects from which we want to extract the partition functions by these Fourier series. So the point is, if these guys here are then meant to be local sections of that line bundle, which we are about to define, then they need to be, then the change from patch to patch must be of this form. That is, there are some functions which are defined here by, of the coordinates xi, xj, which then multiply, well, a section in one patch, yielding the section in the other patch. The point is to describe what are these functions here. And the claim is they're very special ones. They're difference generating functions, namely basically defined by the changes of coordinates that were defining the H-bar deformed complex structure. So I have to speed up a little bit, perhaps. So what's the point? The point is really the very possibility to do such Fourier series representations. Well, this is equivalent to these tau functions satisfying difference equations. So there's obvious periodicity with respect to check variables, and there is a kind of difference equation. If we shift the unchecked variables, they spit out the exponential of the checked variables. So this is, if you wish, deformed special geometry. Now, the coordinates which we consider here are such that this change of variables can be solved to get the check in terms of unchecked variables. And then, yeah, the change of variables on the level of the tau function is given by some function Fij, which, in order to ensure that in the both charts I and j, we have these properties, that is the possibility of this expansion, or equivalently these difference equations satisfied, well, we need shift relations for these transition functions of this form. So if we shift xi, it spits out the exponential of the conjugate to xi, and if we shift xj, it spits out the exponential of the conjugate to xj. So this is, well, there's the obvious relation or similarity to generating functions, except we have replaced taking derivatives by taking finite differences. Here's a basic example that I shall skip for reasons of time. So it is just worked out how to compute such a thing in basically the basic case of a flip to which in the end of the day everything reduces. We find something expressible in terms of the Barnes G function, or it turns out you can also express it in terms of Rogers-Stein logarithms. Okay, so I have to come to some conclusion, but yes, maybe I shall more or less manage. So here is the summary then of what we did for these class sigma cases in the recent paper that is on the archive, that appeared on the archive in April. So there is some work in progress which works out. I mean, there we basically work it out in some basic examples like 4-punctured square, and well, in some work in progress, we will generalize to other cases. So this is to explain how to define the solutions of the secondary Riemann-Hilbert problem by basically combining free fermion conformal field theory methods with the exact WKB used basically in the way I explained. So let me stress some features of the output of that. So first, well, I stressed the importance of going beyond just the case of triangulations, namely to include the cases which have Jenkins-Tribbles differentials and which define a pan-stick composition. And the proposal covers those. What is important, and that is technically the hard part, is then we need to also describe the change of coordinates between Fock-Gontrov, Fenchel-Nielsen, and so to go back and forth. So we need to enlarge the picture into this. Turns out Fenchel-Nielsen is really a close relative of Fock-Gontrov. In some sense, you can see it as a limit by the juggle of Galliotomur-Neitzke of those. Anyway, wherever available, that is on these real slides represented by Jenkins-Tribble, we can compare in some cases with topological vertex computations and find perfect match. And secondly, important work of Itzlisovy and Tücki for the 2-punctured square case with irregular singularities has pointed out there is a strong coupling expansion of the tau function. And well, our proposal covers this. This in particular serves as motivation to, from the other point of view, to extend to Fock-Gontrov type coordinates. So the point is that in our proposal, the exact WKB for quantum curves fixes the normalization ambiguities, and therefore the H-bar deformation in this scheme is as canonical as possible. Good. So here is the concluding slide. There are some more like takeout slides that you could ask for if you want. So there's a bit more you could look at in discussion. But anyway, I want to conclude by saying that the high genus corrections in the topological string theory on X are encoded in a canonical H-bar deformation of the moduli space of complex structures on the mirror Y of X. And there are some hints that this picture may generalize beyond the class sigma examples. And I want to stress in particular, and maybe if I'm given one more minute, I can say a few more words about that. There is a very intriguing relation to the work of Alexandrov, Persson, and Piolin on the geometry of hypermultiplet moduli spaces. And furthermore, the relations I mentioned already to the program of Tom Bridgeland he is currently running. And there are some, and this is embarrassingly the part I understand the least, hints that also it is related to the proposals of Marcos Marinho and collaborators, what we are doing here. But this is somewhat, yeah, annoyingly quite unclear to me at the moment. Anyway, very quickly, let me say something on the relation to Alexandrov, Persson, and Piolin. What they have proposed is they have proposed a geometric scheme for NS5 brane corrections to the geometry of hypermultiplet moduli spaces. And the point is they have come up with something which is very similar, and I believe essentially, at least in the example we're looking at, well, identical or well equivalent to what we're proposing here. So they have proposed to describe quantum corrections using twistor space geometry by Dabou coordinates. And then by combining mirror symmetry, S-duality, and twistor space geometry, they proposed that the correction for one NS5 brane is encoded in locally defined holomorphic functions H and S5 of coordinates xi check. So there's also some Dabou coordinates, polarization, and so on, having an expansion of this form. And of course, well, this looks familiar. This looks like exactly what we have seen and what was playing key role in our approach. And then furthermore, they observed that using the Donaldson-Thomas Gromov-Witten relation of MNOP, the coefficients here, in fact, should be identified, at least for this class where it's applicable, with topological string partition functions. So this suggests that, well, on the one hand, I mean, I think this hasn't been pushed. It hasn't been applied very much yet because there were some open questions about this proposal. I think at the very least our results can be taken as a confirmation of this proposal in an interesting class of examples. And from our point of view, I would take then the relation to this APP framework as a hint that there's a good chance that this picture generalizes beyond the class of examples we've studied. And maybe here I shall stop and thank for your attention.
Thank you, Joerg. Thanks so much for this beautiful talk. Now I'm going to unmute everyone, and then please give a big hand to the speaker. Okay, so we're going to take questions now. Please use the raise hand option. Edward Witten has a question. I have sent you the unmute.
I'm afraid this is a question that should have been better at the beginning of the talk. I don't understand the framework in which what makes one hope to put the topological string partition function in this framework. What is it that points us toward this generalization of this twister-like construction, for example? I know it's a ridiculous question, I'm sorry. You're muted, I'm afraid.
Sorry, you're muted? Yeah.
Okay, now, well, concerning the framework, yeah, as I tried to explain on one of the first slides, the way we arrived at this proposal was indirect and winding, in the sense we really tried to bootstrap ourselves up from cases where we know the result, which then we were trying to interpret geometrically. So it was based on the cases. I mean, we were starting from the cases, and that was the first paper where associated to 4-punctured sphere, that is NF equals 4 theory, where we can compute in some channel with a topological vertex. Good, there is, we observed there are flop transitions, which would then modify the result by some factors. And we were starting to ask ourselves, what is the deeper meaning? What is sort of a geometric picture behind? There ought to be, and that is of course something that topological vertex cannot easily provide, also a representation of the S-duality of the NF equals 4 theory, which corresponds in terms of conformal blocks to the usual channel duality between S and T channel. Furthermore, then we looked at other examples like the pure the pure SU2 theory, where also topological vertex computations are available. But there again, what you get from the topological vertex would not cover the whole moduli space of complex structures. There is the so-called strong coupling region. And then using the relations to the free fermions and the tau functions and the result of Itzlusov-Tukey I mentioned, well, it was observed that, yeah, on the one hand, what seems to be the case, or what, I mean, it was sort of phenomenological observation. So in the cases associated to weak coupling, we could attribute, I mean, the coordinates related to this would always be of the Fenchel-Nielsen type, but in the strong coupling region, the coordinates which play the same role in the sense of appearing in these Fourier series expansions, interestingly turned out to be of Fock-Gontroff type. And okay, so these were sort of the starting points, and thinking further in this class of examples about a geometric picture which would naturally encompass all these cases and combine them into one natural geometric object, one natural geometric structure, led us to the proposal I was presenting here.
Sorry, you're muted. Edward, you are muted. Okay, so we have two more questions. One is from Mina Aganasik.
Hi, Joerg. I'm afraid my question is very elementary. Why would you, could one do this for the original geometry of the topological vertex? In other words, not take some four-dimensional limit, but stay within the original framework? Even there, it seems that you're giving a new reformulation of the theory. So.
I believe so, yes. Of course, somehow the interest here arises, sort of this becomes interesting only when you have, say, some webs or some glued vertices which are interesting enough, which have loops and so on, such that you have all these moduli and so on, which play the crucial role in this proposal. Right, but on the other hand, I think it's sort of the canonical next step to take is to do this, say, for toric Calabials, some interesting class of toric Calabials, and I would think that there are some partial results by Jimbo and collaborators, and a recent paper by, anyway, there appears to be simply a Q deformation of these tau functions, which would then be the basis for doing a similar story as we did in the toric case. And I think, yes, it would be very natural and very nice to do that as one of the next steps.
So in these toric cases, in a paper with Digraph, Marino, Klein, and Waffa, we did have the paper that, not the topological vertex paper, but the one after, we did have a way of sort of quantizing these quantum curves, except what it did not give, it would give basically open string amplitudes only, and never just the purely closed string ones. So firstly, it will be obviously very nice to have this, but it seems that this, if there's a natural setting for your story, it should be that, not these theories where you have to take limits and so forth.
Can you still see my slides? This is sort of the last of the takeouts.
Oh, okay.
Which basically addresses exactly this. So, which also has a nice relation. Can you see the slides, or shall I?
Yes.
Okay, so well, maybe I can make it even a little bigger. Good. So, indeed, you can go from the purely closed string situation to an open closed background by inserting the brains that you invented or that you found. And yes, I think this is sort of really very nicely playing with this picture, and especially this free fermion representation. And I think here is sort of the natural starting point for clarifying the relations. So what I think I can say is, well, first, we do have already a generalization. Okay, here we stay maybe in these class sigma, that is geometric engineering examples, but I think here really, yeah, you have the starting point to go up and go 5-dimensional or go toric. Well, the point is that simply there is a generalization of this formula on the level of the tau function, where you then consider free fermion expectation values. So they have a similar representation where what appears then here, what replaces the thing here on the right-hand side would be expectation values of degenerate fields of Virasoro algebra. And I believe these are the guys, I mean, really these fermions in your paper with Digraph and Albrecht and so on, these fermions are these degenerate fields, really. I think it's clear when you also, I don't know, there was more recent work, for example, by Sergei Gukov and collaborators relating this to the geometric engineering of the surface operators and so on. I mean, this is the story I'm talking about. And yeah, so there's again, you see, there's again these two dual pictures, right? The really B-model picture is here. This is quantum, you have wave functions and so on. And it is this metric transformation which basically brings you to the dual picture here of Digraph, Holland, Zulkowski, and Waffa, which then makes it all classical and really introduces free fermions proper. So here in particular, the psi would be then the solution to the Riemann-Hilbert problem, which plays sort of the crucial role, which in turn then, in our case, would be determined by exact WKB and so on from the quantum curve. So yeah, and this is sort of the other part of the coin here. I would then, so you have here basically as this basic object, this solution to the classical Riemann-Hilbert problem that you have in this context. And well, this is of course what then basically is created by introducing the surface operators or their geometric engineering by your brains. Then in this way, you're making visible the fermions, the open string sector makes this visible and so on. But again, I think it's very important conceptually then to notice this transformation, which is really the transformation between sort of the quantum world in which these fermions are getting quantum, so they have this wave function story and so on, and the classical world where really we have then a classical solution to the Riemann-Hilbert problem on the left-hand side. Okay, well, I don't know if this was useful.
Well, okay, so anyway, this sounds wonderful, and it will be really great to work this out. And these what you call the 5-dimensional cases, I think are even more natural than this setting. In particular, you don't have to take any limit, and they're also related to conformal field theory, right? Well, not to deformations of conformal field theory. So.
Mm-hmm. Okay. Sure.
Okay, thank you.
Okay, we have basically. I think we have time for one more question. So I think next is Arnav.
Okay. I have 2 questions actually. So yeah, we'll see how that goes. One is shared by Andy Neisky, so he can follow up if I'm not clear enough. These locally defined holomorphic functions T of x and x hat that he frequently referred to, are they actually globally defined holomorphic functions just defined in terms of local coordinates that are changing, or sections of lines, or what are they?
Okay, they could well have an analytic continuation to all of this space, but that is not really so crucial for this type of game, because really what we're doing is to decompose the moduli space we're working on according to these types of Stokes graphs. And just for each of the, say, patches or charts defined thereby, we need the coordinates, and well, we need them to extend just enough such that, say, in the neighboring patch associated to different type of Stokes graph, there's another coordinates, and that we have an analytic change of coordinates between them. So this is here for this game the more crucial aspect. So therefore, I mean, of course, these are not new coordinates. These are coordinates that Andy et al. Have studied a lot, except that I would like to stress that perhaps a bit more attention than before can be devoted to these Fenchel-Nielsen type coordinates.
Right, so my question is precisely not about the coordinates. Usually in this wall crossing game, you have smooth interpolating functions in which you can express it in terms of locally defined coordinates that are jumping around, but there's still something global and smooth that interpolates that all together. I was hoping this function T might be of that sort. Maybe that's not clear in the story yet.
Well, the functions T again are a priori locally defined, but they do have, in the examples that we study, they do always have analytic continuation basically to the whole moduli space. So in this sense, they're global, but I mean the crucial bit again is of course how they transform from chart to chart. I'm not sure, maybe actually I had a difficulty understanding acoustically what you were saying, but I hope nevertheless to have addressed the question somewhat.
So sorry to interrupt the engaging discussion. So I think we need to start setting up our next talk. So perhaps probably we can keep discussing in the private